Hello everyone. So in this video we are going to talk about the analysis of Krushkal algorithm. We have discussed both the algorithms so far, the Prim's method and the Krushkal method to find out the minimum spanning tree. But, so now we'll analyze its running time so that we can in a position to compare the performance of the two algorithms. So this is the algorithm that we have used for finding the minimum spanning tree using the Krushkal method. So we'll go through step by step to find out the cost of each step to get the final cost of this entire algorithm. Now here you can notice that we are uh, doing two tasks mainly in this method. One is, you can say, the task one that we are doing is sorting the edges in ascending order, and the task two that is mainly involved in this algorithm is uh, for identifying the each edge, uh, means for the vertex that actually uh, a part of each edge, we need to find out, or we need to apply the find set and union operation. So for each edge we do the union and find operation. So these are the two main tasks that we are doing in the entire algorithm. So we need to find out the cost that is actually required for these two tasks. Now if you look at this, the entire algorithm, we can find the cost of each statement. So let us segregate the entire steps into parts. So this is all initialization step where we are initializing our set which is empty initially. This is, you can say, constant effort. We go one, and then we have for each vertex we are having here in the given graph we are doing a make set, and the cost for this is big O of V, where V represent the vertex set, the set of all vertices, and then we are doing the sorting of these edges in the ascending order. So if we look to the sorting cost, so we can we can do any merge sort or quick sort, which is assumed to be a efficient sorting technique, and the cost for this is n log n, where n is the number of element. So here we are sorting the edges, so we can say the cost is big O of e log e. Then here we are doing the find set and union operation. So we need to find out the cost of these find set and union. Now we have to do these find set and union operation for e number of times. We have to do this for all edges. Now if we consider even a simple disjoint set data structure, now in this part what we are doing, we are doing these operations for each edge. So here we can say we need to perform big O of e operations, and we need to do two find operations and also possibly one union for each edge. So if you consider any of the simple disjoint set data structure, such as disjoint set forest, or we can use union by rank method, then it can be done in big O of e log v time. So we can write this as big O of e log v time. Now one thing to understand here is that for any graph, the number of edges can be always less than equals to the vertex square. So if you take a fully connected graph, and if you find out the number of edges that exist in the graph, it will be either less than or equals to the v square. In general, for any connected graph, the number of edges will be v minus 1. What does it mean? It means if you have three vertex, let's say 1, 2 and 3, then we have two edges. But then what is the maximum possible of edges, then you can take this one edge, then this one edge, one edge, one edge. You can make self loop also. So here you can see this is 1 2 3 4 5 6. Similarly, you can take any graph and you will try to find out that what are the maximum possibility of number of edges. Then you can find that it can go up to maximum v square. So if we now when we talk about finding the running time, we can replace the small values with the larger values. Means if there is a if there are two values to be used, and then replacing the small value with the largest value will not harm, because we are always looking for the worst scenario, we are looking for the at most scenario. So if you look at this term, whenever you find e or v, we can replace interchangeably. So because e is always less than v square, we can always replace v with e, because e is having the more than v here. Okay, so if I take the log both the sides, so if you say log e to be less than 2 log v, so you can say that log e can be replaced by log v. So we can write the total cost of this is big O of 1 plus big O of v plus big O of e log e plus big O of e log v is equals to that. So these are the two major components that can be written as, or you can write this as big O of e log e, that can be written also. This will be big O of e log e. So this is how we can find out the running time of this. So it will give you big O of e log e. So we have get the running time big O of e log e for a Krushkal method of finding the minimum spanning tree. Now we have some variation also. We can also discuss this with the different data structures, and we see the performance. So let us analyze in more detail. Okay, so let me clean this. Now here you can see that we are doing two tasks in general. One is sorting the edges, and the second task is doing this find set and union operation. Now when we do the sorting, now sorting, we are assuming that it will take uh, n log n time, and this is the best performance that we have so far by using a merge sort or quick sort. But if we assume that the weight that is assigned on these edges are existing in a small range, then instead of using these n log n algorithm, we can also use the non-comparison based algorithm, which will be uh, cost of big O of n. So instead of taking an algorithm which will go up to n log n, we can also use non-comparison based algorithm whose running time is big O of n. But this is only possible when we assume that the weight assigned on the edges are existing in the small range. So depending on the nature of the problem, so if we are assuming that the state, if we are assuming that the weights are actually of varying nature and it can be existing in a broad range, then we will be going with the n log n, and the cost will be big O of e log e only, where e is the number of edges. And if we assume that the range is small in the given graph, then you can also take this cost as big O of e. Now in case of the second part, this is for task 1, the cost, and for the task 2, where we talk about uh, applying the find set and the union operation. Now it all depends on the data structure that we are going to use. So if we are using a simple list for uh, for uh, for the implementation, in that case the cost will be big O of n. So here you will be doing these operations find set and union for this number of time, uh, e number of times you are doing this operation find set and union, and it will be costing big O of v and big O of v if you are using a list data structure. But if we use any disjoint set data structure, then this running cost can be improved, or you can say this cost can be reduced. So in that case, this cost will be of log b and log b, or you can say now E is we are doing for each edge, and this is the cost we are finding for find set operation and union operation. So here you can see that the cost can be reduced depending on the data structure that is actually given to you. So here this cost will be only possible when you are using some disjoint set data structure. So in these cases we can frame our total running time. So one is if you are doing the sorting with this, so you can say this will be sort time. The cost will be dependent on sort time plus edge traversing into the find set time plus union operation. So the sort time can be big O of E log E or big O of E, and this can be E into, depending on what type of data structure has been used, this will be either big O of V as a total or big O of log V. So if you go with the list, then this is the performance that you get. If you go with the disjoint data, if you go with disjoint that set data structure, then you will get this. So here you can see that the cost that you can get is big O of E log E plus E into, or you can say E into V, or big O of, if you use this one, or you can use disjoint data structure and disjoint set data structure. In that case, the cost will be this one. So it all depends that which data structure has been used. So in general, when we are implementing the Kruskal method, we are using a disjoint set data structures to get a better result. And normally when we talk about the running time of Kruskal method, it is said to be E log E. So if nothing is mentioned to you and it is asked that what is the running time, you can by default take it this as a E log E. Otherwise, if a data structure is mentioned to you, then accordingly you have to find its running time. For example, if it is given that you are allowed to use only the list for the implementation of this application, then the running time will be different. Then you have to go with this kind of calculation. Okay, so this is all for this analysis, and next we will discuss about the analysis of the Prim's method. Thank you very much.